A very good day, everyone. My name is Marvin from Universiti Teknologi Malaysia, and for my presentation, I'll be presenting this paper titled Automated Guided Vehicle Robot Localization with Sensor Fusion. So this is my presentation outline. So first we'll head into the introduction, and next is the methodology, which will describe the hardware designs of the test AGV which was used in this experiment and the experiment setups. And next is the results, which will discuss about the UKF and EKF methods which were tested on different tracks, and finally the conclusion. For introduction, automated guided vehicle or AGV is an automated solution applied in various industries in the modern days. So the problem with these AGVs are its navigation and path planning, which will affect the performance of the AGV to carry out its tasks. So this is where sensor fusion comes in, which is used to combine data from multiple sensors to improve the perception and localization of the AGV, hence improving the overall functionality of the AGV. So for sensor fusion, we have one of the more commonly used ones would be EKF and UKF, or extended Kalman filter and uncentered Kalman filter. EKF creates an estimation by linearizing using Jacobian matrix, whereas for UKF, it uses uncentered transformation instead. Moving on towards methodology, what we have here is the testbed AGV which was used in this paper to carry out the experiment. So as you can see, it is a two-wheel differential drive mobile robot with few sensors attached to it. Among the sensors include line follower module, which enables the AGV to follow black lines or tracks, which I'll describe in the next section later. And next, we have a 9° of freedom IMU, or initial measurement unit, to provide orientation and motion data to the AGV. And next, we have encoders attached on each side of the wheel of the AGV to provide angular velocity data of the motor. Then next, we have the LiDAR, which is used to provide measurement for the positional data of the AGV. We also have Arduino Mega as the microcontroller to control the overall operation of the AGV, which includes controlling the sensors and then the actuation of the AGV. And finally, we have the processor, which is a Raspberry Pi, to collect all the data and then process the data with the sensor fusion algorithm program on it. Then at the bottom, you can see there's an equation which describes the mathematical model of the AGV's kinematics. Next, on the experiment setup is the tracks as previously mentioned. So we have three different tracks here: track A, track B, track C, which is used to test with the AGV on its localization and navigation. So we have track A here, which is a simple square loop track which involves turning in one direction at each corner. So the AGV will turn right at each corner to complete the loop. And then we have track B, which is like track A but with a slight twist there. So it does not only involve one direction but turning in two directions. And it also involves a small U-turn there, which provides a slight challenge to the AGV. And track C being the most challenging track for the AGV, which is a figure 8 track, which involves sharp turn at the corners of the track, and it also involves turning in two directions. So the AGV will be using the line following model to follow the track, and as the AGV run on this track, various data from the AGV will be collected and processed with the sensor fusion algorithm to create an estimated trajectory or odometry. Next, moving on towards result, we have the result of testing EKF and UKF with encoder data only on track A and track B. So as you can see, this is the odometry, estimated odometry generated by EKF and UKF. Moving on with results, we have the residual value generated from the test. So as you can see here is a residual plotting of EKF and UKF on track A and track B. So on the residual plotting, you see a blue line indicating residual value generated by UKF algorithm, and the red line indicating residual value generated by EKF algorithm. So what is residual? Residual is the difference between the estimation and the actual. So for this case, it will be the difference between the estimated position generated by EKF and UKF and the actual measured position of the AGV. So as you can see from the result, the average residual generated for track A is 0.47 cm and 0.89 cm for UKF and EKF respectively, whereas for track B, the average residual value generated is 1.2 cm and 1.69 cm for UKF and EKF respectively. So that said, the lesser the residual, indicating the closer the estimation is towards the actual, indicating that it is more accurate estimation. So based on the residual values from both track, UKF is 24.07% more accurate than EKF. Next for result is the next test, which includes not just encoder data but also IMU data and LiDAR data to the sensor fusion algorithm. The tests carried out on track A, track B, and track C, all three different tracks. So from track A to track C, with increasing turning difficulty for the AGV led to greater deviation on odometry plotting, as suggested by the IMU and encoder data, which is indicated as green line and black line respectively. For encoder data, the deviations were caused by wheel slip at each turn made by the AGV. So as you can see on track A, the black line indicating encoder data there, it's bad, but not that bad, the deviation when compared to track C. Track C is the worst because track C have the most challenging turns for the AGV. For IMU, however, the deviations were caused by inherent susceptibility of the IMU sensor to the noise. The noise causes the IMU sensor output to drift over time. For EKF and UKF, the estimated odometry by EKF and UKF, deviations are mostly compensated using LiDAR as the measurement. Moving on with results, we have the residual data generated from the tests. So on the residual plotting, the blue line indicates UKF and the red line indicates EKF. So for track A to track C, with increasing turning difficulty, the residual value generated by both UKF and EKF also increase. Hence, it corresponds with the deviations as observed in the odometry plotting. So, based on this plotting, for all three tracks, track A, track B, and track C, UKF generates lesser residual value compared to EKF, indicating that it made a more accurate estimation compared to EKF. Finally, for conclusion, as observed from the tests, UKF performs better than EKF at generating accurate estimation. It is shown that UKF generates lesser residual values compared to EKF throughout the test. And for deviations, like the wheel slip, it's mostly compensated using LiDAR as a measurement parameter in the sensor fusion. And then the IMU used in this test, however, is susceptible to inaccuracies and noise. So for my future work, perhaps by using better quality IMU would solve that issue. Also for my future work, why do I collect all these residual values? Because these residual values can be used for fault detection. And for my future work, I'll be using these residual values with algorithms like SVM for fault detection. That's all for my presentation. Thank you everyone. Thank you for your time. Thank you for listening. And also, I would like to take this opportunity to thank UTM, my university, for the research grant, and also CRES for the R&D grant. And also, I would like to thank our collaborator, TF Automation Sendirian Berhad, for providing us some insight regarding AGV. That's all. Thank you, everyone.